So let's see. You have your most fun problem set due Thursday. In a break, all break. And also I'll be doing some training. So there'll be a lecture on Monday, but not on Wednesday next week. We'll try to find some time to do a makeup for that lecture. But there will be an assignment in 2 weeks that will be shorter and less intense than the next assignment. But this assignment that you're working on is a really, really important assignment in terms of all of the conceptual pieces. So I encourage you to really just try to think about it. I mean, I know there's a lot of cranking out and plotting stuff and tedium, but that's stuff. By the way, of course, everyone knows where you're moving into a new building, and the transition happens right after fall break. So the week after fall break, we're here, sort of. I mean, we're moving offices, those of us who have our offices here, but classes will still be here the week after fall break, and then they begin in Pais, our new building, accent on the I, what did the French ever do for us, or whatever. That's where we're going. And we'll start there on the 21st, I believe. Yeah.
You're going to email out link with your
Yeah, I don't even know it myself. Yeah.
Are these desks staying here?
You want to take one with you? You want to throw them off the roof? I think we need, like, everyone, I think, should have the opportunity to take a sledgehammer to the thing they hate in this building. For me, will be the toilet in room 12. That was, I can't wait to just, for that to go. But, you know, you can decide, and that's fine with me. If there's a fire in here, I won't complain. So the answer is no, they're not going. All right. But you'll miss this building, doesn't it, when you're... Oh, yeah, remember? No. Very good. All right. So, last time we started introducing our most important things, which we'll be discussing it in some more sophisticated ways over the course of this academic year. And so this is our first foray in thinking about damping in quantum mechanics. It's a very important problem. And so we just began that by just saying, in the same way that we do in classical mechanics, we just introduced phenomenologically a damping term into our oscillators. Okay? So we said that there's two characteristic decay times, or decay rates, the times associated with decay along what's called longitudinal decay, if you think about the block sphere as having a longitudinal and transverse direction. So there is a longitudinal decay rate 1 over T1 and a transverse decay rate 1 over T2. By the way, I had these signs backwards. It kind of crazy. Someone was trying to derive some things. I fixed that in there. Anyway, but I'm quite sure these are correct now. Right. And so from the point of view, as we know, these components of the block vector are related to the components of the density operator, right? So the components in the xy plane of the block sphere are related to the coherences, that is the off-diagonal matrix elements of the density matrix. And the component along the z-axis is related to the populations. It's the population inversion, the difference between the population in the excited and ground state for this two-level atom. Okay? Again, it's really important to be able to go back and forth between all these different representations that we have. We have the block vector, we have the density operator, we have the, the probability amplitudes, and they're all interrelated, and it just takes a little bit of time to get used to it, to be able to kind of go back and forth between all these different representations. Okay, so the T1 time is related to thus something having to do with the decay of populations, or the population difference coming to some steady state in the presence of whatever is causing this damping. And the T1 time is related to the way in which the coherences decay. And of course, coherences are measures of the quantum superpositioniness, my favorite word, of the system. That is to say, how much ability is there to see interference between the two alternatives, in this case being in the ground state and being in the excited state. And as we discussed, those coherences are more delicate than the probability to be in a certain state. Because if there is some process which gives an energy shift, a slight perturbation to the energy shift, that adds some perturbation to the phase relationship in the superposition. And that fluctuation in the phase will, if it's uncertain, if it's random in some sense due to the outside law, we'll talk more about that. As we said, an example, if we had our colliding gas that gave us elastic collisions, those would induce random phases in the superposition and cause a T2 time to be bigger. I mean, smaller, the rate of decay to be bigger. Okay, typically, the T2 time is much shorter than the T1 time, but not always. It's not a rule that T2 has to be less than T1, as we discussed last lecture. We can, if this was somehow suppressed completely, and we were limited only by the decay of a population due to some fundamental, say, spontaneous emission, then the T2 time will actually be twice as long as the T1 time. Okay, but that's not typical. And as we also discussed last time, we can get, when we have what are sometimes called coherent errors, or errors relating to the fact that we have uncertainty in the classical parameters. For example, we don't know what the intensity is at the position of our atom, because the atom is at a somewhat unknown position and the intensity distribution is not homogeneous. In that case, we would say there is inhomogeneous broadening. And if we have an ensemble of different possibilities, a statistical ensemble of different possibilities of those classical parameters, then we would have to average over that. And that averaging will typically also lead to what we would call dephasing. But that dephasing is different from irreversible decay, as you are seeing, if you haven't already seen in your homework, in the context of the spin echo. Let's just talk about that a little bit now. As you're studying in your homework right now, this whole business of Ramsey separated zone method, which was developed by Ramsey in the context of thinking about clocks, atomic clocks, but now is a kind of workhorse, a technique that is the way in which one measures the coherence time in a quantum superposition between two quantum states. And so importantly, we can do this mathematical mapping where we think about the two orthogonal quantum states like two paths in an optical interferometer. And our favorite interferometer to draw is the Mach-Zehnder interferometer, where we think about the two paths as like two quantum states. Okay? And as we had seen, the output of this interferometer, if these are 50-50 beam splitters, would be given by something that looks like this, multiplied by the spectral density here. So if I had a monochromatic signal, where this was just a delta function at some frequency at some intensity, then I'd get, interference fringes where I get all of the light out when delta t is 0, and then I would get periodic fringes. Yes, Sam?
We're getting a mega, right? Not a cow.
Yes, indeed. Thank you. Absolutely. But if I had an inhomogeneous, that's to say I had some kind of light here that had some spectral spread of frequencies, then I have to average over that, and my interference fringes would not go on for an arbitrary path difference, L1 minus L2, and we would call this the coherence time, as you studied in one of our first homework assignments. Right, when we looked at this, we had a Lorentzian distribution, we had okay, you remember that homework? Not me, we did that. Right, but the point here is now this is equivalent, this picture is equivalent to thinking about where I map the 50-50 beam splitter to a pi/2 pulse on the Bloch sphere. So I think about the two states now. I can think about this as two quantum states. Let me call them here G and E are the two paths. This path of the light we'll call G, and this path of the light we'll call E. And so a 50-50 beam splitter is equivalent to something which takes G and puts it into a superposition of G plus E, right? And so that is equivalent to rotating around some axis and putting it into the equator. Now the axis around which it rotates in the equator depends on whether this is symmetric beam splitter, it's coded on one side, different from the other. The phase, whether I rotate around the x-axis or the y-axis or some other axis in between, depends on, you remember our beam splitter had a transmission and reflection amplitudes here, and depending on what these phases are, depends on the axis around which I rotate. But let's just say it's around the x-axis for simplicity, okay? So then I go and I'm along the y-axis, right? So then I propagate for some amount of time, and that propagation for some amount of time is a stage of free evolution. Okay, let's call it T1. Well, I don't want to call it, let's call it tau 1. Another T1, all right? So what happens on the Bloch sphere during that time period?
Stays in the equator.
Stays in the equator. But does it just stay there? Does it stay fixed? Well, it depends. I didn't say what the frequency is of the light. So let's say that this is detuned. And let's say the detuning is negative. So the light is not exactly on resonance with the two-level atom. Our two-level atom here has some resonance frequency and I'm detuned by some amount below resonance. So what happens to the block vector? It precesses in the rotating frame. Okay, so while relative to the oscillating laser, and you better have a good lock on your laser frequency to know that the next pulse is going to have a certain phase relationship relative to the first pulse. That's kind of hard to do, but it's easier to do with a microwave or something like that. So now during this period, this guy precesses, and it precesses with that angle delta times time. That's not delta time, that's a delta times tau 1, right? Now I have these mirrors, and those mirrors flip. What was going here is now going this direction, right? So I'm sorry, this is G and this is E. Now we flip them, right? Now this direction, this E goes to G and G goes to E. That's equivalent to a pi pulse around that axis. A pi pulse takes E to G and G to E, yeah.
So this is like, does it matter in our Mach center where we put the mirrors, right? Because like, so I guess I'm thinking we'd want the precession time between the beam splitter and the mirror to be the same on each path, or is that not important?
It is, in this case, we want to make this mapping equivalent, then yes. And then whatever phase, difference between them is an additional difference in phase here. So I'm going to flip this now, do a rotation around the x-axis by pi, which puts this guy on this side. Now, try to draw it a little bit better. With the same angle, delta times tau 1 over there, okay? And now I have another path difference for time for an amount of time t2. It does another precession. So at that point, what happens? Well, I started here, right? And now I'm going to precess. And I continue to precess in this direction. So now my guy makes an angle delta times the difference in those times. Yes, sir.
About the middle block diagram,
Uh-huh.
if you think about it with the associated block vector.
Yes. This is the block vector.
Yes, where the z component is 0.
Yeah.
Q. If the initial xy components are called qx and qy, after that pi pulse, it becomes qx comma minus qy. Is that right?
Yes.
So from that point of view, how can I understand that what is happening is an interchange of E and G?
Because it is a rotation around the z-axis on the block sphere by pi. And that, so if I think about it, not in terms of thinking about the components, but thinking about it geometrically as a rotation, then I am rotating around the x-axis by 180 degrees. And what that does is exchange puts this here and this here, and flips that axis. So think about it geometrically.
Okay, so it does both of those things.
That's right, it does all of that. Of course, there is no x or y component here, it's on the z-axis.
Yes, but if you think about it in the Q way, then you can kind of see that that's how you get the minus
You can,
T2.
if you like.
Because it's like changing, it's not changing cosine, the sign of cosine and sine, it's just changing the sign of the sine.
That's correct. But I think I encourage you to think about it geometrically rather than algebraically. Because I think it's easier to get confused. That's just my opinion. So what's happening here is I'm rotating this whole sphere by 180 degrees around this axis. And that's what happens. And I don't have to keep track of what sign is what. I just look at it as a picture. That's my preference. Okay? Now, this guy, I'd like to continue. Let's now move to the situation where this processes by a certain amount, T2. Now it's coming closer to this axis, right? And now in the final situation, I do a rotation by pi/2 around the x-axis again. And what happens there?
Like down towards the ground.
That's right. And so what will happen is I will have this guy sitting close to the South Pole with an angle here, which is delta times T1 minus T2, or tau 1 minus tau 2, right? And so I ask you now, what is the probability to be in the ground state at this final time? Which is equivalent to what is the probability of coming out this output port of my Mach-Zehnder interferometer.
Plus cos, yes, absolutely.
So as I relate the components of the block vector, right? Because the W component, you remember, the W component of this is minus cosine of that argument, right? And the probability to be in the ground state is 1 minus W over 2, which is exactly this, right? Now, if, on the other hand, there is some dephasing or decay of the system, then what's going to happen? Well, what's going to happen is during this time, not only does it precess, but the coherence decays, right? And then decays again. And will be something that's closer to this. Which means that the probability, let me maybe draw that above here. The probability to be in the ground state at that time is going to be 1 plus cosine delta times tau 1 minus tau 2 over 2 e to the minus tau 1 plus tau 2 over the T2 time. So, what that means, if in the absence of any inhomogeneity in the system, if I look at what the probability to be in the ground state is when these two times are equal, when tau 1 equals tau 2, that is equivalent to a interferometer that has equal path lengths, then what do I expect? Well, if I had no decay, it should be 100% probability to be back in the ground state, right? Because I rotated by pi over 2, I then did this flip, and I go back to the ground state. So with 100% probability, I would get back to the ground state when these two arms of the interferometer are equal. But the fact that I don't see 100% in the ground state is a manifestation of the fact that something must have dephased. And so by measuring the height right here, I can measure the T2 time right here. Moreover, this is a white light interferometer. A white light interferometer is one that which, if I have equal path lengths, it doesn't matter what the color is. It will have 100% constructive work, right? It's independent of omega, okay? Similarly, if I have a spread in detunings, this is like a white light interferometer, okay? And in fact, that's the whole business of the spin echo that you're studying in your homework right now. So let's just quickly do that to make sure everyone understands what's going on in the context of the spin echo. So let me try to draw this again a little bit more. All right, so let's say during this time here, we have two different precessions. I have omega A, tau 1, and delta B, tau 1. So there are two different possible detunings. If it was this detuning, it precessed by this amount. If it was this detuning, it precessed by that amount. Is that clear? Okay. Now I put on this pi pulse. What is going to happen? It's going to flip this around this axis by pi, right? So what does it look like? Well, what it looks like in that case is the guy that was over here is now over here, and the guy that's over here is over here. Right? Everyone clear on that? Okay, so now I let this thing propagate again for this amount of time. And what's going to happen? Well, they're going to keep precessing, and they're going to precess, let's say that tau 1 is equal to tau 2. So I have a balanced interferometer. What's going to happen to these two things? They'll come right back to where they started. They'll come back over here. This is what's known as a Hahn, after Erwin Hahn, who invented this spin echo. The way I like to think about it is the following. It's like I'm starting a race. I have all the runners starting, but they're different speeds. Some are faster and some are slower. The faster one gets ahead, the slower ones are lagging behind. And now I blow a whistle. Turn around. And they all turn around. And they go the other way, back towards the finish line. At this point, the slow pokes are put up ahead, and the fast guys are put to the back of the line, but they're running at exactly the same speed. And they'll all get back to the starting line at exactly the same time, and that's the echo. Okay? And that's what we would see in a spin echo Ramsey interferometer, a Hahn spin echo interferometer, and we would be able to measure the T1 time that is not due to the T2 time that's not due to inhomogeneity, but due to the true irreversible decoherence. Because if there was friction in the problem, and some of the runners are slowing down at different rates, we won't be able to time reverse that. Okay, so there's a part of the dephasing that is reversible, and then there's a part of the dephasing that is irreversible, and by using this kind of formula, we can measure that explicitly. Yes, sir?
Is that irreversibility why you can never see T2 star in the block equations?
Well, I would, to put them into the block equation, I would certainly put them into the block equation.
T2 star?
Yeah, but I'd have to do that in a statistical averaging, right? So I would take each one of these components would be for some specific value, say, of intensity or Rabi frequency of detuning. And then I would statistically average that over that distribution and see some additional decay of, say, the coherences due to that inhomogeneity. This, as written here, are the block equations ignoring the inhomogeneity, but we'd have to put that in by hand. Yes, Sam?
Could you do something like a spin echo if the inhomogeneities like were changing in time, like the atoms were kind of moving
that
around?
would work. Yeah, it would. If you don't have Markovian, you know, if you have something that was fluctuating in a non-stationary way, it wouldn't work. It wouldn't work. That's the problem.
Then is it just normal decay equation? Then it would just be a normal T2 time because you couldn't reverse it.
I wouldn't say it's normal T2, it's a different kind of noise. That's non-Markovian, as we would say. And we wouldn't be able to extract it in this way. But I mean, people worry about those kinds of things. Different noise processes lead to different decay. Normal T2 is really exponential decay, and that wouldn't necessarily be exponential. All right, great. Hope that if you haven't gotten all that, that helps you a little bit with your homework as you're pursuing those problems. Right, very good. So, because I'm a good professor, I've actually kept the equations up here for a change. And what we just discussed over here. Oh yeah, so good. There is another keep. All right, never mind. As we were just discussing, these equations can also be thought about as equations for components of the density matrix, right? Because there's an intimate relationship between the components of the block vector and the components of the density matrix. So I can rewrite these differential equations as differential equations for components of the density matrix, and that's what's known as the master equation. The term master equation is kind of arcane. It has to do with classical statistical physics and thinking about dynamical equations for probability distributions, and this is kind of the quantum statistical physics version. That's where the term master equation comes from. Well, anyway, it doesn't really matter. We just call it master. The master equation is the dynamical equation for the state. Okay. Now we saw in the earlier part of the lectures, earlier in the semester, that the Schrödinger equation, the equation for unitary evolution, was this, right? I called that the von Neumann equation, as it is sometimes called. So this is just the Schrödinger equation, okay? But, as we know, the Schrödinger equation is time reversal. So, and this is irreversible. Therefore, this can't be the full equation for the density operator in the presence of decay. There has to be another term, a dispositive term, which I'll call L. Okay? For liability. All right? So this is going to be our general form of this, our mass equation. Let's look at the specific case of our two-level atom here. And let's look at, for the two-level atom, let's remind ourselves that T1 is 1 over the spontaneous emission rate So if I have an atom in the excited state, it will, the probability to stay in that excited state will decay exponentially with a rate gamma. It's also known as the Einstein A coefficient. And what is T2 in this case? So if I have this two-level atom here, the E and the G is not decaying, but the E is, with some rate gamma. What's T2 in this case? 2 times T1, right? Because 1 over T2 is equal to the rate of, as we discussed, plus beta for this phasing. If I don't have any phasing and the ground state has infinite lifetime, then 1 over T2 is the rate of decay of the excited state over 2. So this is T2. All right, so let's put that in there. And in steady state, in the absence of any driving, what is W? So if I just started the system somewhere and just let it come to steady state, what will happen to the atom? It's in the ground state. And in the ground state, what is W? -1. Excellent. Fantastic. All right. Very good. So, with that, let us look at the equations of motion for the components of the density matrix. So let's see. Again, we have that U is equal to twice the real part of rho GE, and V is equal to twice the imaginary part of rho GE, or said another way, rho GE is equal to U plus IV over 2. And W is equal to rho EE minus rho GG. And we have this thing normalized in our two-level system. And thus, we have rho EE is the identity, is 1 plus W over 2, and rho DG has a minus sign. Okay? So, let's look at the equation of motion, say, for rho, the population in the excited state. So that's the time derivative of 1 plus W over 2, or it's W dot over 2, which is equal to minus gamma W plus 1 over 2 plus omega over 2 times V. And 1 plus W over 2 is equal to rho EE, and V is equal to the imaginary part, twice the imaginary part of that, which is that minus this minus its complex conjugate over I is twice the imaginary part. EG, yes, not EE, thank you. Similarly, rho GG, 1 minus that, that's minus this. So that's just plus this. And I'm going to, because we always write it this way, and rho GE dot is equal to U dot plus I V dot over 2, which is equal to, given over here, we have minus delta V over 2 minus gamma over 2 U over 2 plus, or that becomes minus I delta U over 2 minus I omega W over 2 plus I gamma over 2 V over 2, which is equal to minus I delta times U plus, or minus I, oh, that's a plus and that's a minus. So that one's a plus and that one's a minus, so that's good. So that becomes plus, good. Doing algebra on the board is a mistake. Okay. And then, you ready? So, and that's of course equal to the complex conjugate of this. Because the off-diagonal elements are conjugates of one another. So, these equations come together to give me the master equation for my two-level atom. They are the equations of motion of the components of the density operator for my two-level atom. Now, I want to return to how do we understand this a little bit more physically. We're going to really get into the first principles derivation of this equation next semester when we have some more tools. But there are some things we can see here that are important that we will return to over and over again as we go forward, which is the following. As was discussed, if I think about the decay of the excited state, says the problem, if I in the absence of any, without the driving, the probability to be in the excited state as a function of time will decay exponentially with a rate given by what we're calling gamma, right? Now, how would we get that thinking about if I have without, so from the Schrodinger equation, the probability amplitude to be in the excited state, if I were a stationary state, would go like that, right? I would just have a phase. And in this case, this is a stationary state. The probability to be in the excited state at any time would be constant. It would not change because this would be a stationary state. An eigenstate of the Hamiltonian is a stationary state, meaning the probabilities are independent of time. So how can we mock up this kind of behavior so that the probability decays as a function of time? What would I have to do to the probability amplitude?
Multiplied by e to the negative gamma t.
That's right. If that were the case, and some kind of thing that was like a probability amplitude, but what this is saying is that the energy eigenvalue now takes on an imaginary part. In the same way that we do in classical physics, when we think about a damped harmonic oscillator, we can say there's an imaginary part to the frequency or the index of refraction in a phenomenological way. Okay? So, this, of course, is not unitary. It's not a unitary evolution. Because in unitary evolution, the total norm has to be preserved. And there, it's not. Right? So this is not unitary evolution. However, let's just see if I were to add such a term, can I recover the master equation phenomenologically? Is it good enough to just add an imaginary part to the excited state? So the excited state is not a stable eigenstate, it's a metastable state. And the lifetime means that there's effectively an imaginary part. Is that good enough to recover the master equation? Let's find out. Okay? So let's go back to our two-level atom. And to do this, and we're gonna, because we have all this thing, let's go into the rotating frame and the rotating wave approximation. We had our Hamiltonian we have written. Like that, right? This is our two-level atom Hamiltonian in the rotating frame, in the rotating wave approximation, right? So now let's write this out in terms of the I have EE So that's sigma plus, that's sigma minus, and then I put in the sigma z as E projector minus G projector. Is that clear? And now I'm going to add in the imaginary part to the excited state. Okay. So this is what I'm going to call H effective. It's not actually the Hamiltonian because it has this imaginary or anti-Hermitian part, right? This Hamiltonian is equal to the Hamiltonian minus I over times H bar gamma over 2 times the projector on the excited state. So this thing has a Hermitian part and an anti-Hermitian part, or an imaginary part. Is that clear? That just came from adding an imaginary part to the eigenvalue of the excited state because it was metastable. It only lasted with a certain lifetime of decays. So we want to see, can we recover the Schrodinger, the master equation, from just a Schrodinger equation with an imaginary part, that is to say, an anti-Hermitian part of the Hamiltonian. Okay? So that is to say, I'm going to look at, all right, well maybe there's some effective Schrodinger equation. And my rho then is just equal to this. Do you think that's going to work? What do you think?
Yes.
Seems reasonable. But there are some principles here that seem like, this ain't going to work for some reason. I'm not sure why yet. But first of all, most importantly, this Hamiltonian is not Hermitian. Meaning that the time evolution generated by this H effective is not unitary. Which means the norm of the vector won't be preserved with time. Because if the norm of the vector is preserved, the math is unitary. So that's a problem. There's another problem, which is this is a pure state. Effective. But we already saw that the damping dynamics took the block vector inside the block ball. And those states are mixed. So something is amiss, yeah.
And also now right eigenvectors are not necessarily the same as left eigenvectors.
Absolutely. So there's all kinds of weirdness that goes on here. However, as we're going to see in a moment, it gets amazingly close. And the way that it gets close and the way it differs is extremely important, as we will see. So let's try it. Let's just see what this equation gives us. let's look now thus at the equations of motion for the probability amplitudes. Just from the short equation, just looking at the, say, the ground state component of this equation. Okay? So what that is that going to be equal to? Well, that's going to be equal to minus I delta over 2 CG minus I omega over 2 CE. And C GE dot is plus I, because that one's got the minus sign. Gamma over 2 minus, I'm sorry, delta over 2 minus gamma over 2 CE minus I omega 2 CG. So these are my couple ODEs. In the absence of the damping, this gives us Rabi oscillations. Okay? So let's look now at the equation of motion of the diagonal element of the density matrix. Which is that. All right, so I just multiplied this by, so I'm going to get plus I omega, that may be that, minus gamma over 2, multiply this by that, I get rho EE, and then I get minus I omega over 2 rho G E. So that's the first term, just multiplying this by CE star, I get CE CE star, which is this, and CG CE star, which is that. Okay? And then I have the other term, I take the complex conjugate of that, and then multiply it by that, and I get plus minus and then I get plus I omega over 2 CG star rho EG.
Can I ask how you got that CG dot equation second line, please?
This guy? So I just took the matrix element in my head without going through the steps. So if I look at this, I'm going to look at the matrix element of the Hamiltonian,
Yeah.
projecting that with the state. So,
Coming from the left, it's okay.
right?
What about coming from it? How do you know what psi effective is?
Psi effective, okay, so now this has psi effective is some amount, so I've just written this in the spaces. Okay, that's how I did it. But I didn't show all the steps. Okay, so putting that, adding these two equations together, what do I get? Well, this guy cancels, this adds together, and I get minus gamma rho EE minus I omega over 2 rho GE minus rho EG. When I put those things together. That looks okay. Maybe there's a sign error, but I'm just not. No, it looks right. It's actually right. Oh my God. All the signs came out. That worked. That looked fine. Amazing. You ready? Or not? Oops. Row. All right, now let's look at rho GE dot. That is equal to what? Well, that is equal to CG, the derivative of CG, CE star. That's the off-diagonal matrix element of the density operator for a pure state. So that's CG dot CE star plus CG CE star dot. Right? So let's put it together. We got minus I delta over 2, that's rho GE, minus I omega over 2 rho EE. That's the first term. Now I have to take the complex conjugate of this and multiply it on the right by CG, so I'm going to get plus I delta over 2 minus gamma over 2. This is a star rho GE. That is a star plus I omega over 2 rho GG. All right, ready or not, add these guys together. I can take the star here, minus. Now I'm happy because that's got to add together. So when I add them together, this becomes minus I delta minus gamma over 2. That looks exactly, that's this equation. So we are getting exactly the measurement, or are we? What have we left out? Let's look at rho GG. The other off-diagonal is just the conjugate of that, so that's fine too. The only element we haven't yet confirmed is rho GG. So let's look at that one. So that's equal to minus I gamma over 2 rho GG minus I rho EG plus complex conjugate. Okay? The complex conjugate of that is plus the same thing. So putting that all together, I get rho g g dot is equal to minus I omega over 2 rho e g minus rho g e. Is that what we got over here? Minus sign is fine, because headed in the other direction, rho 1 is eg minus ge. However, there's one missing thing, which is that term. And what does that term represent? That's not decay, that is refeeding. That is to say, when the system starts in the excited state and it decays, it goes to the ground state. And we somehow didn't account for that here. How could we do that? Well, you might think, why don't I just add a plus? Instead of having that, I'll have something which has that. And a positive imaginary part to this, which would somehow make that grow. But that's not what this is. This is not gamma times rho EE, because that would be exponential growth, which would make a runaway. This is not exponential growth. It's refeeding. In fact, there's absolutely no way. It's a fundamentally different process, as we will see. So we can get damn close to the master equation by just adding an imaginary part, but we can't take into account the refeeding effect that happens under spontaneous emission. As we will see, that is a fundamentally different kind of effect. And thus, what we have is the following. My master equation evolution according to a non-Hermitian Hamiltonian plus refeeding, which is a fundamentally different effect.
When you were, deriving, for example,
Yeah.
rho E, and it involved something times something star plus the complex conjugate.
Yes.
And then you said this is minus the same thing. But that implied that the row was Hermitian, namely that it had real diagonals. But if we're throwing out the hermiticity of the Hamiltonian, can we also posit that the row is non-Hermitian?
Well, what we were asking at the moment was, could we recover the master equation through this evolution of a pure state through a non-Hermitian Hamiltonian? So we're asking ourselves, if I just evolve the pure state according to this Hamiltonian, can I get those equations by writing the density operator this way? In other words, does this non-Hermitian evolution, non-unitary evolution of a pure state recover the master equation? Now, this operator is Hermitian. Moreover, it would be meaningless to say it wasn't, because the density operator is just a vehicle for calculating the probabilities of measurement outcomes. And thus, according to the Born rule, it must be a Hermitian operator. Otherwise, it's a meaningless operator. So this was the question we were asking ourselves. Could we get, if I just look at this equation, I'll come to your question in a moment, second. So, this is an operator way of expressing what we just did in terms of probability amplitudes. We're asking, does this operator equation, which has just a slight modification, I'm going to call this H effective prime, where the prime is just the fact that I have the dagger here. Does this equation recover these equations? The answer was almost, but not quite. Yeah, Sam, you had a...
Oh, yeah, I was just wondering, I mean, isn't it already kind of meaningless because it's not normalized, so it's not really, you can't really think about it in terms of...
Well, it's a good question. So, you're right that there is a fundamental problem here, is that it doesn't stay normalized. So it seems, we know that it's not going to work.
So it's like it's traces.
But it could, this in fact is a fine description of the following problem. Let's say I have a 3-level atom. Okay? And let's say that this level only decays to this, but doesn't decay to that. Okay? But I'm able to drive this somewhere. And I just look at the subspace of the Hilbert space, that is those two levels. I could do that. The density operator in this subspace will not be, the trace will not be preserved, because population is leaving this subspace and going to that subspace. That's perfectly legal. So preserving the trace of a subspace is not required. What's required is preserving the trace of everything. Okay? So this would be a perfectly good description of this system. Yeah?
Is this a general formulation for any open quantum?
It is, and we're going to see that. In fact, so what I wanted to conclude with in my grace period of 2 minutes is to say that the true master equation will have this form. there is going to be the term that is related to the decay, which can just be modeled with a non-Hermitian part to the Hamiltonian. So H effective here in our problem was H minus I gamma over 2. So I add this imaginary part, but I have to add this additional defeating term. And a general form is as follows. So, this is what's known as the Lindblad form, after somebody named Lindblad, of the master equation. H I have what are known as Lindblad or jump operators. I'll call them L for Lindblad, and I have there's some number of them. This is some index. My H effective is H minus I over 2 sum over mu L mu dagger L mu. And the Lindblad form then is the following. This is the Lindblad form of the master equation. These are the repeating terms. So for example, for our two-level system with spontaneous emission, there's only one Lindblad term, and it is the square root of gamma times sigma minus. Why is this called the jump operator? It's called the jump operator because, well, that's not sigma minus, that's sigma plus. Now it's good. Because this takes the system from the excited state to the ground state when the system undergoes a quantum jump. And it's those quantum jumps, those stochastic jumps, which our continuous decay cannot properly take care of. That's a fundamentally different effect. That is a stochastic process. That's different. And if I look at what this repeating term is in this case, so that is equal to the square root of gamma G rho G E times the square root of gamma. So that's L dagger. Then this is gamma, so do the other way around. So you notice that that refeeding term puts stuff back into the ground state depending on decay from the excited state. It's that plus gamma that feeds the ground state from the excited state through these jump processes. Now, I ask you to store this in your memory for a semester, because we're going to come back to this and derive this from first principles and see how we can think about the master equation as a kind of combination of non-Hermitian but continuous differential equation with decay punctuated by stochastic processes that are related to quantum jumps that refeed. And the combination of these two gives us the whole equation. Yes?
Another question. So since the Hamiltonian is not Hermitian
Yes.
anymore, so what happens to the observable quantities? So is there any problem with measurements?
No. So firstly, there's a few different things I would say. Firstly, this is what we call the effective Hamiltonian, meaning it's the Hamiltonian that appears in this dynamical equation. So it tells us how to evolve the quantum state based on the dynamics that's happening. But it doesn't say anything about measuring anything. Because if I want to now say I do a measurement, and I do a measurement of an observable, well, that observable is whatever I'm measuring, and it doesn't become non-Hermitian. The non-Hermiticity here was related to the fact, as you said, we had an open quantum system. Because our quantum system was not just the atom, but the atom coupled to the electromagnetic vacuum, and we didn't keep track of what was going on in the electromagnetic vacuum, we had this irreversible decay. But what quantum mechanics is a formalism for doing is telling us, how do I calculate the probabilities of measurement outcomes? Well, I have to update the state based on what I know. And if I know it's interacting in a certain way, I would update my state in time according to not the unitary Schrodinger equation, but now I would update it dynamically according to the master equation. And then I would use the Born rule, as I always have used the Born rule, to calculate the probabilities of measurement outcomes. Except that in this problem now, the system, the off-diagonal moments will decay, it'll become a mixed state. So this, by the way, is trace preserving. And it also is something that would, doesn't necessarily preserve the trace of rho squared. So I can start with a pure state, and over time, become a mixed state due to that, and we're going to talk a lot more about all those things.
If we cannot avoid vacuum fluctuation,
Yeah.
means that we always have mixed states in quantum mechanics?
Well, we do. I mean, unless the time is sufficiently short that we can neglect it, but we can never neglect it exactly. So, it's like asking, can I get to zero temperature, right? I can get close, but I can never be exactly at zero temperature, right? So I never have exactly pure states, but I can well approximate it as such. Yeah?
Well, what happened to that second term in H
Yeah.
effective, and then over here, you write, to the right of you, you write H effective is H minus Lindblad?
No, I get it. So this is equal to minus I over 2 L dagger L. For the specific case we have over here, this is L. If I write this as L dagger L, I get that term.
So L is this scary thing, but when you take L dagger L, it goes back to that.
That's right. It's not that scary, it's just sigma minus. It's the thing that takes me from the excited state to the ground state. But sigma minus times sigma plus is the projector on the excited state. Lots of food for lots of thought. Have a good lunch.
Can I ask?